All right, I hope this thing's on. Let's give a try to this pretty cool technology. So I just want to give a quick proof of a lower bound on the extremal number of KST, the complete bipartite graph with classes of size S and T here. Okay, so we already know from previous session that this is at most, or the order of magnitude at least above, n to the 2 minus 1 over s. Okay, this is when s is the, well, it doesn't matter. It holds for 1 over s and 1 over t, but we're going to say this here. Okay, the smaller s is, the better upper bound this gives here. Okay, and the theorem we're going to prove is a simple lower bound with a probabilistic method proof. So the theorem says, let's fix t is greater than or equal to s is greater than or equal to 2, and then we have that the extremal number of KST is at least, we're going to write 1 over 8 n, and the exponent here is 2 minus s plus t minus 2 divided by s times t minus 1. Okay, so it's a little bit uglier than the upper bound there, but it's one of the best lower bounds that we have in terms of the exponent here. They're not matching though. This is an open problem to close the gap on the two of them here. And so how do we prove something of this nature? Well, we need to construct a graph, right? So I need to construct a graph that has no KST in it and has approximately this many edges in the graph there and has no KST. Okay, and we'll prove this with a random graph. So I'll generate a random graph, massage it a little bit to get exactly the property that proves this theorem here. Okay, so let's say build a random graph with edge probability, right? When you're building a random graph, the edge probability is the most important thing. The edge probability will be p, and p is going to be 1/2 n raised to the, this is pretty common in these problems here, the exponent is going to look reminiscent of this guy here. It's going to be negative s plus t minus 2 over s times t minus 1. Okay, you have to think a little bit for a moment here, but the values of s and t are large enough so that this exponent will be negative. So this, you can think of this as form 1 over n to the something. Okay, so p is truly an actual value that makes sense for a probability. Okay. All right, so once we've got this, let's compute a couple of simple expectations. So the expected number of edges, right, in a random graph here, you have n choose 2 pairs of vertices, and each pair has this probability p of actually being an edge. So the expected number of edges is exactly p times n choose 2. And for the purposes of this argument, we're going to say that this is at least 1/4 p times n squared. Right, n over 2 is more like n squared over 2, but it's less than that. So if I put another 1/2 in front of it, I'll get an upper bound there. Okay. Also, I want to know the expected number of copies of KST. So we can produce this random graph. We have an expected number of edges. We also have an expected number of KSTs. Okay, so we're trying to have none, but we have an expected number, and that is, so expected number of KSTs. I'm going to give an upper bound here, and I'm going to give a really crude bound for it here. So how do you build a KST in your graph? Well, of the n vertices, choose s of them to be one of the classes. Then of the remaining n minus t s vertices, choose t. It's an upper bound, so I'm just going to write n, choose t. Okay. And then what does a KST look like, right? You have s vertices here, t vertices here, and every edge is present. So in order for every edge to be present, this probably needs to come up s times t many times. So p times s times t. Okay, and I'm going to do a little extra computation here. This is at most, we'll have some crude bounds here. N choose s can be replaced with n to the s over s factorial is an upper bound on it. Let's just take n to the s over 2. And this is n to the t over 2. Okay, so I can rewrite this as, actually, do I want n over 2? Yeah, let's write this. So this is going to be at most 1 over 4 n to the s plus t times p to the s times t. Okay, that's an upper bound on that, on those guys there. Okay, so I want to further massage this guy here into something that's workable, that resembles this quantity here, so we can do a little bit of computation at the end. Let's rewrite this as, let's move it up here. So this can be rewritten as 1/4 n to the s plus t times p to the s plus t, s times t minus 1 times p. Okay, I'm just pulling 1p off of the thing there. And let's further compute this. So this is 1/4 n to the s plus t. I'm going to put the p right here. That p, I'm going to move it over here. And then I've got p, which is this guy here. I'm going to rewrite that. We'll take it as an upper bound here. So I'll take the 1/2. It's 1/2 raised to the s plus t minus 1. So that's something much smaller than 1/2. So I'm just going to replace it with a 1/2. And then I've got the leftover n to this whole mess here. But think about this. N to the negative s plus t minus 2 over s plus t minus 1 raised to the s plus t minus 1. The s plus t minus 1's cancel with each other. So I get p raised to the negative s plus t minus 2. That's what's left over when I take this n raised to that power. And remember, the 1/2 here is that 1/2 that's out front of that. And technically it's raised to s plus t minus 1, but I'm replacing it with just the 1/2. Okay, and then notice what we have here. I have 1/8, right, the 1/4 p, and then what's the exponent of n? S plus t minus s, this should be in parentheses, right? That was what was on the top here, negative the whole thing. So in parentheses, the s's cancel, the t's cancel, negative, negative 2, so p n squared, okay? The expected number of edges is 1/4 pn squared. The expected number of copies of ks is 1/8 pn squared. So the two resemble each other very much so. Okay. All right. So now what am I going to do? Let me erase here, and then we'll use these. So I want to keep these two expectations because they're handy. So I'm going to erase this guy here. It's slightly harder than I expected. So this is at most 1/8 p n squared. Okay. And the proof's almost done here. Okay, so we're going to define a new random variable for this set of random graphs here. So let x be the random variable that counts the following. It counts the difference between the number of edges minus the number of KSTs. Counting number of edges minus number of KSTs. Okay? So you produce your random graph, you count up the number of edges, and you subtract from it the number of copies of KST. That's just some number, right, for any given graph. So it's a random variable. Okay, so now by linearity of expectation, what do we have? We have that the expected value of x can just be written as the expected value for the number of edges minus the expectation for the number of KSTs. Okay? But this expectation here is greater than or equal to what? This quantity, so it's the number of edges is greater than or equal to that, minus something smaller than it. So when I combine the two together, I get that the expectation is greater than or equal to 1/8 p n squared. Okay? Good. So that's the expected value of this weird expectation here. Now, how does the probabilistic method work? So by the probabilistic method, I'll say it like that, but let me explain this in a little bit better words here. The expectation is the average value of this random variable here. So think about it, every graph can be produced by this random graph process, right? No matter what graph you imagine, it can happen with this edge probability, right? All kinds of graphs are possible. Some are more likely than others, but all are possible. This is the average of value x across all those graphs. That means that there exist graphs whose value of x is at least as large as this. If all of them are strictly smaller than this, then this is not the average, right? Okay, so probabilistic method, there exists a graph, an n-vertex graph, but a graph G, such that the value of x for G is greater than or equal to the expected value. Okay? This also means there exist graphs whose random variable is at most the expectation, right? This is the average. When you have an average, you have values that are at least it and at most it. Of course, that allows for all values to be exactly equal to it. So this graph is going to be a good candidate, because what I'm going to do, construct G prime as follows. Construct G prime by removing an edge from each KST in G. Okay, so you produce G randomly, and G has X, at least the expectation, so at least this value here. Now that graph may have KSTs in it, of course, all right? We know there's the expectation. We don't know how many, but it has some. I'm going to remove an edge from every single copy of KST. If you have a KST, like this guy here, and you remove an edge from it, it's no longer a KST, right? It looks like a KST minus an edge. So it's not a KST anymore. How many edges have I removed there? Well, one for each of the KSTs. But I know that the number of edges minus the number of KSTs, in other words, minus one edge for each KST, that quantity is at least this on average. And our graph here was one that had X at least this average here. So what that means is the number of edges in G prime is exactly the value X that came from G here, which is at least 1/8 P n squared. Okay? And now, if you plug in for P, this exponent here, what do you get? Well, P is 1/2 n to the that. So that's where my 1/16 comes from in the statement of the theorem. And then n, what is the exponent? It's 2 from there minus this business here. S plus t minus 2 over s times t minus 1. And that's the end of the proof. Okay? All right, so I hope that makes sense. What's the rough idea here? It's a standard probabilistic proof argument here. I create a random variable. I compute an estimate on its value here. I know that if its I know that there exist graphs that can be produced through this random method whose random variable for x, its value, is at least the average, at least the expectation. So take one that beats the expectation, or is at least the expectation, and that from that remove all the KSTs one by removing a single edge. And we know, because this records this value here, we're left over with still quite a few edges, at least this many edges, which comes out to be exactly our quantity there. And this resulting graph G prime has no KSTs. Okay? Sometimes this technique is called the alteration method, right? I used a random method here, not to produce the graph that I wanted, but to produce a graph that was close, and then I altered it by removing or changing things to give me the graph G prime that had one I wanted. Okay, great.